Hello. Are all Gong show participants sitting here in the front rows or in this area of the auditorium? Hello. Are all Gong show participants, are all Gong show speakers sitting around here? If you're not, please sit around this area so that we expedite the coming in and out of the stage. So every person will speak for 4 minutes, and then there will be half minutes for questions. And then at 4.5 minutes, the gong will sound, and you have to leave the room for the next speaker. So, OK, so now we are ready to start. And we have Sandeep Ghosh, and he'll be telling us about quantum information measures for restricted sets of observables.
Yeah, can you hear me? Hello. OK, so thank you very much for the opportunity to give this talk here. So in my 4 minus epsilon minutes, I'm going to explain what the title means. OK, great. OK, so let me start by introducing the main question which I want to ask here. So suppose consider a completely general case where you have a quantum mechanical system in some state psi. And suppose there is an observer who can actually probe this state with some set of simple operators, which I call this set. So which I call this set A, which is a linear span of some set of operators. Now, simple or complicated really depends on the specification of the problem. But here you can think of these as corresponding to, let's say, some coarse-grained degrees of freedom, say in some low-energy effective field theory example. And moreover, I will consider the case where this set of operators is not closed to form an algebra. And so basically in this case, using modern parlance, what you can say is that equivalently, the observer has access to only a code subspace of states, which you get by acting with these operators on the basic state psi. And I'm presuming that the observer doesn't know about the details of the full Hilbert space of the theory, which could be something complicated. And for me, the set of accessible observables will be spanned by the following set of two-point functions. Okay, and it is also important to assume that there are no zero-norm states within this code subspace. And then I want to ask the following question, that can we define measures of quantum information in this case to actually, in some sense, quantify the entanglement in this state psi, which I guess is somewhat actually misleading terminology. But in any case, since you can think of this set of observables as forming, as providing a notion of a subsystem, and in that case, you can ask that when you're, you can ask that if you're focusing only on a subsystem, then there is a certain uncertainty in your knowledge about the state of the system, and can you quantify that using quantum information measures? Now you may ask that why am I considering sets of operators and not algebras? It seems that this case is actually relevant for a purpose study of entanglement in theories of gravity, where you're also naturally led to consider sets of operators rather than algebras, because at some point of time, if you start considering actually sufficiently complicated products of operators, then in that case, you have a situation where actually sharp notions of locality start to break down. Okay, so let me take a few moments to introduce the cast of characters in my story, but I really don't have to introduce them into anymore. Because you have heard about these things. So basically, in this case, the main players in the game will be these modular and relative modular operators, which you have heard in Witten's lectures. And so from this slide, I don't have to explain to you anything more. You know everything which you need to know about these operators. The only thing which I want to mention is that I will define these modular and relative modular operators for my case with respect to the code subspace only, and I won't require to define them in the full Hilbert space of the theory, which will suffice for my condition. So you also know from Witten's lectures that there is this very nice algebraic definition of the relative entropy, for example, which is the particular quantum information measure which I'm going to look at. And so therefore, which is this hierarchy relative entropy. But it turns out that when the set of operators is not an algebra, in that case, the hierarchy relative entropy is not actually a good quantity to look at. It can in some cases fail to distinguish between states. And actually the following thing can happen, that the hierarchy relative entropy for sets can vanish when the two-point functions of my accessible set of operators are not the same in the two states. So here I propose that you can consider the following set, or actually the following, so actually a new set of actually quantum information measures, which you can think of as actually kind of cousins of the relative entropy, and which are defined in this manner in terms of a certain in terms of the operator norm of a certain quantity x, which is this particular combination of the modular and relative modular operators. So let me just actually point out that there is actually good reason is that there is good reason to believe that these are actually good measures of distinguishability between quantum states because of the following properties, that this is invariant under a change of basis for your set of operators. This measure is in general actually kind of positive always, and it only vanishes when the set of all 1-point and 2-point functions of elements in this set A are the same in the two states. More importantly, this measure is monotonic in the sense that if you reduce the number of observables at hand, in that case, this measure actually goes down. And also has this property of insularity, which says that if you couple your system to some auxiliary system whose degrees of freedom are actually completely not correlated with the system being observed, then this measure of distance does not change. And the last example, which I want to flash, is that you might think that what is all this good for. So here is one application of it, which is in the study of a coarse-grained version of subregion dualities, where you may ask that if you specify a certain set of simple operators, here there is a natural notion of simple operators in this case. Okay. Okay. Yeah, so yeah, that's the end. Yeah, so basically you can read this slide on your own. Okay, let me flash the conclusions.
So laser stop.
Next, yeah.
Okay, perfect. Okay. I want to thank the organizers for the opportunity to speak. So today I'd like to describe some things I've been working on, trying to relate entanglement of purification and bit threads. So the first thing I want to do is describe what each of these are. So entanglement of purification of AB is an information theoretic quantity, which is related to minimizing over all possible purifications of the density matrix AB. And in general, it's extremely difficult to calculate. In the past year, there's been a proposed holographic dual to this quantity, which is found by first determining the entanglement wedge of AB and then determining the minimal cross-section of this entanglement wedge. Bit threads are a reformulation of the Ryutaki-Nagi formula, where we've turned the minimization problem into a maximization problem. So first we define flows, which are norm divergentless vector fields. And then we ask how much flux can we possibly put through or on A through the manifold. And the entanglement entropy is given by this maximum flux. And it turns out that where the threads get as close together as possible is at the minimal surface, which then acts as a bottleneck. So what we would like to ask is, can this framework be extended to describe entanglement of purification? So the necessary modification is one additional constraint in the optimization. So what we want to do is put an explicit von Neumann boundary condition, which forces the threads to remain inside the entanglement wedge. So by placing this, there is no way that the threads can go outside, and they have to remain in here. And it is known that there are many inequalities which relate entanglement purification to quantities such as entanglement entropy, mutual information. Of this list today, I'd like to focus on this first one. So an explicit construction is known of 1/2 of the mutual information, and it is also known that this construction of this flow remains inside the entanglement wedge of AB. So as a result, when we optimize to find the entanglement of purification, we know that this mutual information flow will be one of the allowed flows. So as a result, the entanglement purification is bounded below by 1/2 the mutual information. Similarly, if we consider the flow which will give us the entanglement entropy, we realize that the entanglement of purification flow meets the correct boundary conditions. So when we're optimizing to find the entanglement of entropy, this is one of the flows it's selecting from. So in order to get this entanglement purification flow to be maximal, again, we have to impose these additional boundary constraints, which will force it to remain inside the entanglement wedge. So because constraints can only reduce the maximum in a maximization problem, that implies that the entanglement of purification is strictly going to be less than the entanglement entropy. And I should note that of the list of all the other inequalities I listed, this procedure works for all of them. The only additional thing you need to add is potentially monogamy mutual information. So this procedure is very robust for describing how to relate entanglement purification to these other quantities. And then some future directions, it's possible to re-describe this without having to refer to the entanglement wedge, but it adds additional flows. And then I'd also like to consider covariant generalizations and situations where we have more than one region on the boundary. And then there's also this new quantity called minimal modular entropy, which has relations to entanglement purification. Thank you.
I didn't quite understand the definition in terms of the threads of the entanglement of purification. Was it in your picture?
Oh, yeah. So that's this slide here. So what we're saying is we are now we're taking these flows and we're saying of the possible flows, we only want to consider those which remain inside the entanglement wedge. So there's no flux of these threads across the boundary of the entanglement wedge. So you're basically taking this feasible set of all flows and then reducing it to a set that you want to consider over.
All right, I'd like to thank the organizers for the opportunity to speak. I'm going to tell you about entanglement constraints from topological linking based on this preprint, and it's joint with all of these authors. So it's an old idea to try to study quantum entanglement, say in a pair of qubits in the EPR pair, using topological entanglement, say in the pair of circles in the Hopf link. So one way you could make this question precise is you could ask, is there a formula or a bound for the entropy of states in topological quantum field theories where knots and links make an appearance? And the answer is yes, an upper bound on entropy does exist in Chern-Simons theory for a certain class of states, and the goal of this talk is to tell you about this bound. So we're going to prepare our states using the Euclidean path integral on a 3-manifold with n torus boundaries. So you can see an n equals 3 example here. And the Hilbert space that these states exist in will be the n-fold tensor product of the single torus Hilbert space. So we could choose a lot of different 3-manifolds, but we're going to consider something called a link complement. So we start with a link in S3, and we drill out tubular neighborhoods of each embedded circle in the link, essentially replacing each component with a single torus boundary. Then a link complement state is just the result of the Euclidean path integral on this manifold. And the coefficients of such states are actually topological invariants of the link that we began with. So now we choose a bipartition A and A bar of the link components, and this induces a bipartition of the Hilbert space. Then we just compute the entanglement entropy across the bipartition using the usual formula. And I've written the explicit partial trace here. And we need one more concept to talk about the bound, and that is the idea of a separating surface. So consider a link in S3, a separating surface sigma, given a partition A and A bar, for a sublink LA and its complement, LA bar, is a splitting of the S3 into two other 3-manifolds, MA and MA bar, such that the sublink is in MA and its complement is in MA bar. So you can see 3 examples of separating surfaces of different genuses. The A partition is in blue, and the orange is the A bar partition. So now we come to the bound. Given a link in S3 and a partition, A and A bar, the entanglement entropy across this partition is upper bounded by a constant that depends only on the level and the choice of gauge group, and the genus of the minimal genus separating surface. So one considers all possible separating surfaces for this bipartition, and one takes the genus of the minimal genus one. So you can think of this bound in 2 different ways. You can think of it as the topology of the link providing an upper bound on the entanglement entropy across the bipartition, or you can consider it as the entanglement structure of the state providing a lower bound on the genus of any separating surface. In particular, if a separating surface exists of genus 0, the link is unentangled. So there are a lot of other results contained in this paper. In particular, there's a relationship discussed between entanglement classification under a particular equivalence and a well-known topological classification of links. So you can see the paper for more details. And some future directions are whether we can obtain a lower bound on the entanglement entropy from topology. Only an upper bound was discussed here. and if these entropies have some sort of holographic interpretation. Thanks. Questions? All right, thanks.
Next person. Look at there. Lock hand. Oh, you're here.
It's the red.
Yeah.
Here, this will count down from 4 minutes.
Hi. Hi all. My name is Sagar Lokhande. I'm from Amsterdam. Well, sorry, the slides are not complete. Yeah, this is much better. So I'm from Amsterdam. I'll talk about bulk entanglement entropy in perturbative excited states. This is part of a work with Alex Berlin and Nabil Iqbal. You can use this ID to find the paper online. So in the discussion session yesterday, we had a brief chat about quantum corrections to entanglement entropy. The idea is simple. When you have excited states in the CFT, then the entanglement entropy of a subregion gets quantum corrected in this way. This is the well-known Faulkner-Leukowicz-Maldacena proposal. And the second term here is the entanglement entropy of the bulk matter fields across the RT surface. So we calculated the bulk entanglement entropy for a scalar field in ADS3 in the one particle excited state in the small interval limit. And let me be a bit more precise. In the CFT, we have a primary excited state, and we assume H equals H bar. It's a scalar field in the bulk in the state given by this density matrix. And we worked in the bulk perturbative Hilbert space and using the replica trick in the bulk and taking the limit of n goes to 1 of the Renyi entropies, you get this as the answer. Theta here is the angle on the circle, the CFT. It's a 1 + 1 CFT, and theta is assumed to be small. Delta S bulk denotes the difference of the bulk entanglement entropy in the one particle excited state and the vacuum of the scalar field. And well, H is the conformal weight. So as you can see, it's a simple expression. And once you include the back reaction of the scalar field on the RT surface, the change in the area is given by this equation here. As you can see, the second term in the second equation and the first term in the first equation, they are the same with opposite signs. So the total answer for the change in the entanglement entropy for the excited state in the CFT is the sum of these two terms. And the second term here and the first term there will cancel. And we also checked that the full answer, the sum of the two terms, matches the known expressions. This was first calculated by Gabor and Tomonori a while back. So I'll conclude basically by saying that the one-loop quantum corrections to the area in the bulk and the bulk entanglement term, they contribute at the same order and cancel in a subtle way to make FLM work. There are some open questions that we are working on. I showed the bulk entanglement expression that is known only in the small interval limit, but the area back reaction is known for a finite sized interval. So we would like to understand what is the finite interval size expression for the bulk entanglement. The hard part here is the analytic continuation, because we have the Renyis for finite interval. So this is something we'll try to address in near future. And secondly, the main motivation for the work was to look at the entanglement entropy of perturbative gravitons in the bulk. That is still under construction, and I'll thank you for your attention and my talk. Um, I do not, well, the one particle excited state in the bulk, it corresponds to turning on the primary operator in the CFT. So the holographic, if you are looking for the dictionary, then the mass of the scalar field is fixed in terms of the conformal weight of the operator. And it's a scalar field because I don't have a spinning particle, I don't have a spinning operator in the CFT. So I hope that answers your question. Yeah.
It's next, previous, there's a laser pointer right above that.
Okay, so you will have fun. So my talk will be, never mind. My talk will be about this long title, and it's a joint work with my supervisor, Don Page. And this work is something similar to Giddings' nonviolent non-locality that Ahmed explained yesterday. Okay, so firewall paradox, roughly speaking, just roughly, so the AMPS paradox suggests that we should modify one of unitarity, equivalence principle, and locality. And I'm not going to explain why, but for some reason, we want to modify locality to non-locality. So this is the keyword for my talk. And so in Ahmed notation, this means we give a postulate 2, not no drama. Okay, so then let's study our paper, because it's cool. So we gave an explicit but simplified model for black hole evolution, and also we proposed how to modify locality. And this first part is very good, but at the same time, it's kind of too technical for a 4-minute talk. So for the rest of my talk, I will focus on the second part, non-locality part. And this minimal departure kind of means, well, it depends who you are. But basically, we want to confine non-local effect only into the gravity sector so that there is no contradiction to today's experiment. So it's good. Okay, so this is the last slide. Okay, I should have enough time. Then I'm going to explain the scenario of our proposal. Okay, so this is basically the horizon. This sharp blue line is the horizon. And this is after the page time, so that black hole system is maximally entangled with the rest of the system. And now the key is we do not assume any crazy non-local interaction between inside and outside the horizon, but instead we assume the gravitational degrees of freedom themselves spread non-locally beyond the horizon as drawn in this blue zone. So based on that, let's think an outgoing Hawking quantum which is initially entangled with its Hawking partner, so that now they're maximally entangled and there's no problem of monogamy. But because of this blue zone, this mode can locally interact with this non-local gravitational degrees of freedom, and gradually it picks up the information, and at the end, this Hawking mode have all the information it should have. So yeah, cool. Now the firewall paradox is gone. And well, I mean, of course, this is just an idea to tackle the AMPS challenge. And as Ahmed suggested yesterday, I think we just have to take AMPS challenge to kind of take it as a clue to formulate quantum gravity. And hopefully, we will see some breakthrough in the near future. That's all. Thank you.
Are these non-local effects present in Grinder space?
So, well, we haven't thought about it, but so this effect, this effect is more based on the work by Giddings. So, he basically mentioned that even though two space-like separated fields, they do not commute if you couple to gravity. So we kind of want to see this non-locality from that view. So, okay, I'm not answering your question, but basically I haven't thought about it yet. Any other question?
was added at the last minute because I'd gotten missed out. So.
That's the wrong one. Was yours the key?
No, it should be PPT.
Is it?
PPTX, no. Wasn't it the one above? Yeah, there.
Next previous.
Okay, so this is a paper with Patrick Hayden. Came out on arXiv yesterday, and we call it Learning the Alphabets of Black Holes. So here's the basic setup. We have a black hole in the center of ADS, in ADS CFT. We look at slightly more than half of the boundary region. And there's a minimal surface going through the bulk on either side of the black hole. And so we have this region in the bulk lying in between them that we call little a prime. And the question is, can you reconstruct bulk operators in little a prime from this boundary region, big A? And the answer to the question is, I've sort of been subtle and not told you what the black hole is. So if the black hole is just a thermal ensemble, then little a prime is not in the entanglement wedge of big A. You can't do it. But for a particular pure microstate, then it does lie in the entanglement wedge. You can do it. So how are these two things reconciled? Well, the answer is simple enough. The operator you get when you reconstruct it for a given pure state depends on what the pure black hole microstate is. So we have these state-dependent reconstructions. Actually, you can do slightly better than reconstructing it for one state. Actually, you can do quite a lot better. You can use a single boundary operator reconstruction that works for a large subspace of size e to the alpha s, where alpha is this quantity that's independent of g Newton. And a single boundary operator will work for any subspace of that size. But at the same time, you can't find one that will work for the entire space all at once. And this corresponds in the Schrodinger picture to a thing in quantum information. So we say that region big A includes the alpha bits of region little a prime. So the basic reason for this in ADS CFT is just that's the amount of entropy you can put into the black hole before the entanglement wedge jumps to this surface A2. But there's sort of a more intuitive way to see it in a tensor network model. Mostly I just included this slide because I really like this diagram. I think it looks cool. It took me ages to make. So we have this glowing yellow bulk operator. We want to push it to the boundary. We can do that, but we can only do it by pushing it through the black hole. The black hole is this giant tensor in the middle. You can do that if you have roughly an isometry, but it's only an isometry or an approximate isometry if you don't consider too many states going into the black hole. That's that big red dot in the middle. That's the large amount of bulk entanglement, bulk states. So yeah, final slide is why should you guys care about this? I don't really have time to explain why, so I'm just going to list a load of things. Hope at least one sounds cool enough for you guys to go and read the paper. First is that you can only have alphabets. You can only have this phenomenon if the error correction, the reconstruction, is only approximate. But actually, the error in the reconstruction is a tiny, tiny error. It's a non-perturbatively small effect. But these non-perturbatively tiny errors are making possible these large order 1 semi-classical phenomena. So in fact, because of this, we can put lower bounds on the size of the error in the boundary reconstruction, which is quite cool. More generally, this provides a limit where we can make the Planck scale go to 0, but we still have a very state-dependent entanglement wedge, state dependence of the entanglement wedge at sort of ADS scales. There seem to be some very strong connections between this and the Papadopoulos-Raju proposal you heard a certain amount about yesterday. We're not quite sure of the relationship. There's a lot of strong similarities. We also show that the Hayden-Preskel black hole as mirrors paper can be reinterpreted and generalized as the statement that black holes reveal their alpha bits in their Hawking radiation as soon as they can. And basically, because of this and for other reasons, black holes saturate the alpha bit capacity. So we say the terrible pun of black holes are alpha bit soup. Yeah. So yeah, go read the paper.
Is the claim that the Hawking radiation contains information way before the page time?
No, this is after the page time, but to encode the alpha bits of like a large space of states, i.e. the black hole entropy, you need at least a fraction corresponding to 1 plus alpha divided by 2 of the entropy. Just that's the capacity at which you can send those alpha bits. So it's after the page time, but it's still as soon as possible. There's in fact a duality between revealing that alpha bits in as small a fraction as possible and encoding no information for as long as time as possible.
Also, did you really consider a subspace of black holes arbitrary subspace of the given dimension?
Yes, essentially. Like, you need all the states in that subspace to be a black hole state, but subject to that can be any subspace, I think.
So any subspace would lead to some reconstruction?
Yes. So if you take particularly weird superpositions of black hole states, then you can make stuff. But if you restrict to a sort of random subspace of black hole states whose entropy is almost exactly equal to the black hole entropy, then every state in that will just look like an ordinary black hole. And that's sort of the space that's having its alpha bits encoding. So there is a slight subtlety there, but yeah, we talk about this in the paper. Yeah.
So in terms of what you're calling state dependence, if I understand, can I rephrase it as saying that you have logical operators where which reconstructions of them are possible depend on your choice of code subspace?
Yeah, that's exactly right. But it's overlapping code spaces. So there's a logical operator, the single logical operator in the bulk for the entire larger space of black hole microstates has a lot of different boundary physical operators. And you can always find one so long as you don't try to do it for too large a subspace. But you never can for larger subspaces.
That's the usual thing, right? Is if you include a few more states in the code subspace, then the reconstructions get a little bit worse.
Yeah, it's certainly a general story. What's different in black holes is you have this universality, which is sort of, that's where the connections property Masraju are, because you have that construction for any equilibrium state, but it doesn't work for all at once.
But the representation on the full Hilbert space is not stable.
No. If you have the entire boundary, then you can do it universally. Yeah.
Which, this is you.
Yes.
Next, previous, and laser.
Okay. Thank you. I think now this is my turn. Hello everyone. I'm Koji Yumemoto from Japan, YITP. And I'll talk about some kind of the generalization of Ryu-Takayanagi formula, so-called holographic entanglement of purification conjecture, corroborated with these peoples. And as we have learned from the Marshall-Hedrick's excellent lecture, the Ryu-Takayanagi formula connects entanglement entropy on the boundary CFT with the area of the codimension 2 surface in the bulk ADS. And each implies there is a deep connection between the quantum entanglement on the boundary with space-time geometry. And however, we have to be careful that the entanglement entropy does not represent the entanglement in general. And if the given density matrix is ρ is a mixed state, then it rules the meaning of entanglement and just reduces the von Neumann entropies. So our first question is that, is there any generic relationship between the quantum entanglement and geometry in such a mixed set setups?
So to the answer to this question, we consider generalization of Ryutaka formula by employing the so-called entanglement of purification and conjecture that its holographic duals denoted by these red vertical lines. So this is our conjecture. The entanglement of purification is defined in this way. So you first have a So you first have a density matrices rho AB, which is a mixed state. Then you can purify it, and you have a purified state psi AA prime and BB prime. So the entanglement purification is an entanglement between A groups and B groups in these purified systems, minimized over all possible purifications. And its holographic dual is called entanglement wedge cross sections. And this shaded region is denoting the entanglement wedge cross section corresponding to the boundary subsystems. And the entanglement wedge cross section is the area of these red vertical lines. You can intuitively understand it as a minimal cross section of the entanglement wedge. Okay? And there is several supporting facts of this conjecture. And the first one, which is the most mathematically rigorous one, is that the agreements of the information theoretic properties listed here. And we have a heuristic understanding of why such equivalence happens based on the tensor network descriptions of ADS space. And also, we can reproduce typical behavior of entanglement wedge cross-section, some kind of the phase transition, by that of the entanglement purification in toy models under some technical assumption. Okay, this is my second message. In this summary, we generalize this conjecture into the multipartite setups. So to do this, we first define a new information theoretic quantity called multipartite entanglement purification, defined in this way. And this is a measure of multipartite total correlation, which means that it captures both quantum entanglement and classical correlations, and which is monotonic and strictly local operations. And what we did is we proved the information theoretic properties of this quantity in generic quantum systems, listed as follows. And then we generalized the entanglement wedge cross-section for multipartite setups, inspired by the tensor network descriptions. So, and we showed that all the properties we proved for the entanglement of purification side can be indeed satisfied by these geometrical quantities. So, which motivates us to make a more generic conjecture for entanglement of purification, the holographic entanglement of purifications. And we hope that it provides us a new tools to investigate the relationship, the multipartite correlations in the ADS CFT. Thank you.
I have a question of sorts. The third cut, you might think it would have some kind of back reaction.
So, sorry?
Well, if you go back to the picture where you showed the entanglement of purification.
Okay. So the left one?
Yes.
Yes.
The vertical red line.
Yes.
I guess it has to produce no back reaction for this conjecture.
Yes, yes. In this conjecture, we did not consider the back reaction or quantum corrections.
No, but the question is on the back reaction on the dotted black lines. Because mainly those are branes of the same tension. They're all measuring this entanglement. Maybe they'll have tension n minus 1.
Yes. Sorry, I have no clear answer now. Sorry. So, okay, sorry. Thank you.
Is this your? Yes.
Okay. first, I'd like to thank the organizers for giving me an opportunity to present my talk. So this is a paper appeared a few weeks ago with the same title. So, okay. My very motivation is to study the dynamics of wormholes, like formation and decay and so on. And in particular, I'll be interested in to study them using the ADS-CFT correspondence. And this direction is explored by the Gauss-Jaffer's wall. So their argument is as follows. So they consider the two-sided black hole, which has two asymptotically ADS regions connected by a non-traversal wormhole. And then you apply the double-thread deformation, which composed of the two operators, which lives in the different side of the CFT. So this one is living in this side, and this one is in this side. Then what they found out was that originally non-traversal wormhole becomes a traversal wormhole in the end. You may think that this deformation is a bit unnatural, but it turns out that it can appear naturally from the QFT. And it is natural to consider, to generalize this argument to the case of the single asymptotic region, or the single CFT, not the tensor product of the CFT. So that is what I worked on. And this is my setup. So I consider the CFT2 on the cylinder, and it is dual is a global ADS. Then I deformed the original Hamiltonian with the double-thread deformation, and I put the delta function in T. So this deformation is instantaneous, and only for like an instanton. Then and I also consider the slight generalization of this deformation using the HKL back local operator. So in this case, the deformation pushes inside the bulk, not like this one. So in this case, the double deformation lives in the inside the bulk, but it is still a CFT operator. Then the quantity I will study is the average neural energy. And these are the results. So this is the time directions, and the vertical direction is the average neural energy. And you then found out that average neural energy will become the negative when the coupling G is positive. What this implies is that in the bulk, what happens is there's a time delay in the bulk instead of wormhole, since this state is originally connected. And I also studied this in CFT. So what happens is that from the deformation, there are, in the null direction, there's a negative and positive energy waves are emitted. And then so for the null energy, only this null ray intersecting with this interval because non-zero. So the average neural energy is negative on this region, and the otherwise is zero. And these are I also studied the entanglement entropy and the second linear entropy for the half region. And these are the diagrams. And we found out that this is, they are completely identical behavior. Thank you.
Okay, thank you. I'm going to be talking about this paper with collaborators Adam and Stefan. Okay, so let me explain what I mean by energies entanglement. So start with the quantum field theory and divide the space-time with this null plane into a left side and a right side. Now pick any curve you want, some profile via y, where y is the transverse direction and v is this null direction. This curve defines this right-hand side, the yellow surface, which then I can, if I start with the pure state, I can trace out the complement of the region R and compute the phenomenon entropy associated with that state of region R. Now this phenomenon entropy is going to be a function of the profile V, so I can take two functional derivatives of it with respect to V at positions y and y prime. This quantity will generically have a contact piece, a delta function piece, and I'm going to call the coefficient of that S double prime, and everything else I'm going to call the off-diagonal terms. So this is the statement. In quantum filters with interacting UV fixed points, S double prime is equal to 2 pi times the expectation value of the null component of the stress energy tensor at the point of deformation. So I'm going to be showing this for holographic theories in a special case. And my collaborator in the next talk will explain how this will work in general quantum field theories. Okay, so before let me introduce relative entropy, which is the between states rho and sigma. Let's say sigma is the vacuum. The relative entropy is the expectation value of the vacuum modular Hamiltonian minus the phenomenon entropy of the state rho. The vacuum modular Hamiltonian has a local expectation value like this, which is basically the boost energy on each of these null lines integrated in the transverse direction. So if I use this equation and take two functional derivatives of both sides, I'll end up with this. I get a delta function because this expression is local of the modular Hamiltonian, and I'll be left with the relative entropy second functional derivative. So the statement that S double prime is equal to 2 pi expectation value of TVV is equivalent to the statement that the relative entropy functional the two functional derivatives of the relative entropy has no contact delta function piece. So this is what I'm going to show in holographic theories in a very simple case where there is some coherent state in the bulk that perturbs the geometry, perturbatively changes the geometry from pure ADS. So my region on the boundary is one of these wiggly regions with profile via y, and it will have a corresponding bulk dual region, which is another wiggly region now in the bulk in one higher dimension. So because of this JLMS result, we know that relative entropy could be computed in the bulk by computing a relative entropy basically in the bulk state. So relative entropy, and in a coherent state I can forget about the bulk entanglement entropy. So relative entropy as computed in the bulk will just be the boost energy in the bulk, which is this expression, again a local expression. Now if I take two functional derivatives of it, I get an expression like this. So the T bulk in a given state will fall off like z to the 2 delta if the state is created by operator dimension delta. And if delta is bigger than d minus 2 over 2, this expression, you can show that there is no delta function in this expression, basically. And delta is bigger than d minus 2 over 2 because d minus 2 over 2 is the unitarity bound, and it's only saturated in free theories, but we know that holographic CFTs is not free. But this actually points out that if you imagine delta was d minus 2 over 2, there will be another delta function piece, which explains why this the connection between energy and entanglement will have to be modified for free theories. It's not going to be just S double prime equals 2 pi TVV. There will be an additional term. Thanks. Yeah.
Is there any relation between the null energy condition and the result of the S double prime?
Yes.
Can you
so if you pick a generic deformation and compute the second derivative of phenomenon with respect to that second deformation, you will, if this deformation is a general one, you will not only pick up this the contact delta function piece, you will also pick up this off-diagonal pieces. And the off-diagonal pieces have a sign because of strong subadditivity. They have a sign of their own. Therefore, if for a general profile, the second derivative of S with respect to that deformation will be less than the energy, less than the null energy because of these off-diagonal terms, and that's the null energy condition. Thanks.
this laser pointer or something. Cool, thanks.
Hi. So I'm going to tell you about some work with my collaborators here on entropy variations in defect conformal field theories. So how do I? Oh, OK, sorry. OK, so the main result I'm going to tell you about is the notation's already been set up by Arvind, but the second local null variation of entanglement entropy is always equal to the stress tensor in any QFT with an interacting UV fixed point. So interactions are important here. I'll talk about what happens when you have a free field. So the interacting case is pretty simple to argue. So we start with the replica trick. So you take your quantum field theory, and you make n copies of your quantum field theory, and you get a boundary because of the conical deficit. And you compute correlation functions on this n-sheeted replica manifold, analytically continue in n, take the limit as n goes to 1, and take derivatives with respect to n. So another way to think about this is you have an entangling surface with a twist defect on it, a codimension 2 twist defect. And whenever I bring a local operator close to the defect, it generates an infinite tower of local defect operators on that surface. So if I bring the stress tensor close to the defect, one particular operator that's generated is the displacement operator, which enacts like deformations of the entangling surface. And it's given by a particular residue of the stress tensor where the sum corresponds to Zn symmetrization, which is important in order to get integer spin operators under analytic continuation. So you can get variations of the entanglement entropy just by looking at the 2-point function of the displacement operator in the n goes to 1 limit. But we're particularly interested in the contact term. So if we look at the OPE of 2 displacement operators, we want to know where the delta function comes from in this OPE. So the key point here is that you can write down a representation of the delta function as an n goes to 1 limit of the OPE behavior. So in particular, if the OP coefficient and dimension of an operator have the following behavior, then that operator in the n goes to 1 limit turns into a delta function. So note that the dimension can depend on n because it picks up an anomalous dimension due to the breaking of the conformal symmetry. So the operator needs to have spin 2 and dimension d as n goes to 1. And in an interacting CFT, the only operator that can do this is the stress tensor. And you can use defect word identities to confirm that this behavior is in fact true. Now, in a free field theory, things are a little more complicated. So to start with, there's a simple relationship between the displacement operator and the null energy operator. So if you do the analytic continuation in n, and then deform into the Lorentzian direction, then in the n goes to 1 limit, roughly insertions of the displacement operator look like insertions of the average null energy operator. So in the OPE, in the n goes to 1 limit, in a free theory, you have the stress tensor, but you also have this leading contact term that comes from the OPE of 2 null energy operators studied by Hoffman and Maldacena a while ago. And in particular, it's this non-local spin 3 operator. So basically, the question that you have to ask is what local defect operator gives rise to these Hoffman-Maldacena contributions in the D plus OPE? And we have strong evidence that they come from these double replica defect operators in the free theory. So these correspond to operators that you insert on 2 different replicas and Dn symmetrize. And hopefully they have some relationships to these null ray operators that David Simmons-Duffin has studied recently. Thank you. Thanks.
Hi, everybody. I'm Daniel Brennan. I'm from Rutgers, and I'm going to be talking about things that are a little bit far afield from what we've been talking about so far. I'm going to be talking about something relating to localization, which will be related to some of the talks from next week. All right. So we're going to be looking at expectation values of Tuft operators in 4D n equal 2 theories. You can look at them for a multitude of different reasons, and of course we're going to be using localization, as I said. But the thing is that when you try to do this localization computation, you find a fundamental obstruction to using localization. And so in this project, we sort of diagnose this and propose a resolution to this problem. Right, so we're looking at 4D n equal 2 SUN gauge theories with NF fundamental hypermultiplets on R3 cross S1. And we're looking at Tuft operators, which are half supersymmetric defect operators, which are essentially impose Dirac boundary conditions on the magnetic and Higgs field in the path integral. So these theories are theories of class S. So we can use the AGT correspondence to compute the expectation value of these operators. However, if you want to use this, it doesn't scale very well with increasing Tuft charge, and it also changes drastically with the matter content of the theory. So this is sort of our motivation for trying to use localization to study these theories. So from general rule principles, we know that the expectation value of these Tuft operators decomposes as a sum over monopole bubbling contributions. And in each sector, what you have is a contribution from the bulk fields, and then also a contribution from fields living on the actual defect itself, which you call Z mono. And we're actually just going to be interested in this Z mono term, because that's where all of the problems come from. So monopole bubbling occurs when a smooth monopole is actually absorbed into a Tuft defect. And what happens is that this actually screens the magnetic charge of these defects and deposits quantum degrees of freedom on the defect. And so by using string theory, we can actually determine that it's a n equals 0,4 quiver superquantum mechanics. This is an example of one such quiver for an SU2 theory. And so after resolving everything, adding all the masses and such, you find that there's the moduli space of the superquantum mechanics has a Higgs branch, which is just a collection of points which have a local harmonic oscillator potential. And then you have a non-compact Coulomb branch, which has a finite potential energy as you go off to infinity. This contribution, as I said, Z mono, comes from the defect superquantum mechanics, which you can just write as the Witten index of the superquantum mechanics. And so since we're looking at supersymmetric quantum mechanics, the Lagrangians are Q-exact, so you can use localization. And so by actually going through the whole localization computation, you find this sort of standard localization answer and then plus a boundary term. This boundary term is dependent on all of these parameters, which are supersymmetric deformations of your theory. So that's not good. And so essentially what you have is a problem because it's dependent on this psi, which is an Fi parameter, which you can think of as a regularization of the theory. And it's also not invariant under the action of the Weil symmetry of the flavor symmetry groups. But most importantly, it doesn't match with the AGT computation. And so that's really bad. And also, there's no sort of limit you can take of these extra parameters that would sort of fix the problem. Right, so since there's no beta dependence, you can sort of get rid of it by just restricting to the trace over the BPS states by taking this beta goes to infinity limit. And so by studying this limit, you can actually show that the localization computation omits all Coulomb branch state, BPS states. And so essentially, we propose that in order to fix the localization computation, you have to actually go in by hand and add this contribution by studying the effective superquantum mechanics on the Coulomb branch. And so we find that in all known examples, this works. It's Weil invariant, and it's independent of all these parameters you don't want it to be dependent on. And this is a summary. And so that's it. Thank you. Any questions? Oh. Yeah, so that's, it's a sort of confusing thing, but if you go through there's a very nice brain construction of it, and you can literally just count all of the supersymmetries, and it just happens to work out. I don't really have a terribly great explanation for that, unfortunately, without more details. Anyone else? Oh, thank you.
So, hello, my name is Mikhail Yevtukhiev, and today we'll be talking about studying superconformal symmetry enhancements through indices. So, all right, superconformal field theories are defined in 2 to 6 dimension and in 3 to 6 dimension. Superconformal algebras are described by the number of the supercharges, and the allowed values are as follows. Now, we can study the representation of the superconformal algebras called superconformal multiplets, And it turns out that we can get the full superconformal multiplet from a single component, from a single state, called bottom component, under the action of supercharges. In a general case, all supercharges matter, all states appear, and such a multiplet will be called long. But sometimes, some of the states get a zero norm. And so we have to throw all the zero norm states away, and what we get is a short multiplet. And all the interesting objects, such as stress tensor, flavor currents, they lie in the they lie in the short multiplets. So naturally, one would study superconformal field theory by writing a Lagrangian. However, it's not always possible. Say for 4-dimensional n equals 3 theories, it is impossible to write Lagrangian, so we need some another quantity to study it. And this is superconformal index. Superconformal index captures the short multiplet content of the theory, and it captures it up to a combination of the short multiplets. So basically, sometimes your short multiplets can combine together into a long one. And in this case, they will not be captured by the index. But when this doesn't happen, you have a protected multiplet, and you can figure out whether it is in the theory by looking at the theory index. So right, superconformal index, one of its inputs is the amount of supersymmetry that is in the theory. But actually, we may underestimate the amount of the supersymmetry, and we may write formally a lower supersymmetry index for a higher supersymmetry theory. And one of the options for this to happen is SUSY enhancement at the end of the RG flow. So let us take some superconformal field theory, then deform it, and go to the end of the RG flow. In the end, we may have a SUSY supersymmetry enhanced. For example, Song et al., they have looked at many well-known d equals 4, n equals 2 superconformal field theories. Then they deformed them with n equals 1, preserving deformation, and went to the infrared. And in infrared, they found out that in many cases, there is enhancement back to n equals 2. And in some other cases, they have found n equals 1 non-Lagrangian theories with rational central charges. So they might have been n equals 2 theories. And so to figure out whether there is SUSY enhancement, we have studied the SUSY enhancement condition on index. So the sufficient condition on index can only be related to the conserved supercurrent. And when the conserved supercurrent multiplet is protected, we can write a necessary and sufficient condition. And the necessary conditions, they come from the requirement that our low SUSY index can be written as a combination of the higher SUSY multiplets. And so to sum up, what we have been able to classify all the conditions on SUSY enhancement, and we have found necessary and sufficient conditions in these cases. So basically, in these cases, it is enough to check one term in the index Taylor series expansion to check whether there is SUSY enhancement. And that's what we got in the rest of the cases. And we have also checked some of the d equals 4 superconformal field theories that Song et al. Have found. And unfortunately, they do not exhibit a superconformal symmetry enhancement. Thank you. Come again? Yeah, we did that for the in flat space. Flat space. So I mean, basically, it's all algebraic statements. So as far as I understand, it should not depend on the form of the manifold, but the index computation may change for the yeah. So. No, no. All the statements here are algebraic. So as long as you have the index, you're good.
Laser pointer, forward previous.
Excellent.
Hi, my name is Vincent Min. I'm from KU Leuven, And I want to talk about these two papers. I'll mostly be referring to the first one, but the second one is also related. And both are on the topic of counting entropy of black holes, specifically ADS4 black holes. And you might think, we've heard now a couple of times, that these black holes of entropy, where is it coming from? Are there some microstates? Can we understand them? Can we even count them? And the first headway in answering this question was made by Strominger and Waffa. Famously, they counted the black hole entropy of asymptotically flat black holes, 5-dimensional. And there's been a lot of results that has happened so far. And recently, we've made progress in actually counting black hole entropy for asymptotically ADS black holes. So how does that work? Well, you take an ADS4 black hole. If you make it extremal, which we do, it's supersymmetric. You also get an ADS2 throat. There's also a Riemann surface of Riemann G, which is the horizon. And now you can use holography, twice in fact. There's two ADS regions. And what you do is that you can calculate some appropriate partition function, and you hope that this then reproduces the entropy of the black hole. That's great. It was pioneered by Benini, Zaffaroni, Christoph. So once more the setup, we have a gravity calculation where we have an ADS4, well, it's a solution in ADS interpolating between ADS4 and ADS2 cross sigma G near the horizon. This is the energy direction going to the IR. And we mimic this in the CFT, where you have a specific CFT, it's ABJM. And we put this on S1 times the Riemann surface. And due to the curvature of the Riemann surface, there's now a length scale. You will start flowing, and you end up in a one-dimensional superconformal field theory. Now, we add another ingredient, which is that we do a mass deformation. And you end up from ABGM, you do another RG flow is induced. You end up in a new fixed point, which we denote by ABGM, MABGM. And then you put this theory on a Riemann surface, and you flow downwards yet again. Now, the object that we're interested in is called the topologically twisted index, and it's the log of the partition function of the CFT on this space. And we also do a topological twist to cancel the curvature of this Riemann surface. Now you need to use the machinery of localization to actually calculate this object, and people have managed to do that in the large N limit. So this is the proposal that should now match the black hole entropy, but first these black holes need to be constructed. So we go through the mess of this 4D n equal to 2 supergravity. It has 4 gauge fields, 3 vector multiplets, and due to this mass deformation, it now also has a hypermultiplet, which makes one of these gauge fields massive. You go through the machinery of these BPS equations, you solve them, you find a beautiful solution, and read off its entropy. And then it's the supreme moment. You try to compare, and if you do it correctly, you will indeed find a match, as we did. So this is the main result. We can actually reproduce the black hole entropy, counting these states, in the dual CFT, using this topologically twisted index. This is a very nice result, I think. It's both a check of holography, a very non-trivial check, and hopefully we have learned something about the microstates of these black holes. Of course, there's many questions unanswered. You would want to know what are these specific microstates in the CFT dual to in the bulk. I have no good answer to this question. You can ask, what is this topologically twisted index telling us about the gravity solution other than the entropy? And this is research that is still ongoing. Thank you. A question?
I'm confused about the statement you're in ADS4, because you seem to compactify on a Riemann.
Yes, excellent. I was sloppy in my terminology. It's asymptotically locally ADS4. So really, the metric there is has the Riemann surface in there. Yes, that's so important.
In spatial infinity is a Riemann surface.
Yes.
And I can't quite see what the 3 manifold that fills it in is.
Let me see. The metric.
I guess it just goes in toward the horizon.
Yes, yes, it does. Good. Yes. Other questions? Excuse me, can you speak up? You're absolutely right. Indeed, this topologically twisted index is a function of the R charges, and you might fix them in the UV, but then along the RG flow, the R charges can flow to different values. And you might wonder, what is the IR value of these R charges? And you need to use extremization to get them. We use that.
Is this yours? Yep. All right, great. Laser pointer, forward and previous.
Thank you, organizers, for everything. So I'll be talking about holographic conformal blocks in 2 dimensions. I'm from UCLA. This is work with these authors here. So just a little general story. Witten diagrams give a 1/n expansion of CFT correlation functions in the usual ADS CFT, and vertices are integrated over all of ADS. We know correlation functions that meet a conformal block decomposition. These are just kinematical quantities fixed by conformal symmetry. And one question one can ask is, what is this object that could compute a conformal block in the bulk? An answer is a geodesic Witten diagram. Just take the vertices, integrate them over geodesics connecting the boundary points instead of over all of ADS. So we work in ADS3 where there's a special story. Perturbatively, gravity can be formulated as 2 copies of SL2R Chern-Simons theory, and we'll consider boundary-to-boundary Wilson lines with matter insertions at the end. We construct a Wilson line network in the bulk, which will compute for us correlation functions on conformal blocks. So here is a CFT to 4-point function. We see these conformal partial waves and OP coefficients appearing here. Using conformal symmetry, we can map them to the plane and to our favorite points like that. And we see the 2-dimensional cross ratios appearing here. So here is the object that we want to compute, a conformal block, using Wilson line networks. So here is the holographic construction. This is just a time slice of global ADS. We pick SL2 primaries in the infinite C limit and spin A minus HI representation of SL2R. And we insert these high states at the boundary insertions. And our bulk to boundary propagators are basically Wilson lines. This little a is the SL2R Chern-Simons gauge field in a specific gauge. Generically, there will be a number of singlets in the decomposition of the tensor product of these 4 representations. And our prescription is each singlet corresponds to a conformal block. And what you need to do is evaluate the matrix element between high phase states on the boundary and the singlet in the bulk of this Wilson line network. So what we did next was to consider 1/c corrections. So a path integral over the bulk gauge fields would give the quantum expectation value of the Wilson line network. And in our construction, this corresponds to going to the Virasoro blocks. So a 1/c expansion of a Virasoro block. So to illustrate this, I'll talk about a simpler case. That is the case of a boundary-to-boundary Wilson line, which computes a 2-point function. We consider the Hamiltonian reduction of SL2R current algebra to the Virasoro algebra, and its action on a spin J SL2R primary gives this Virasoro primary of the specific dimension. I expand it in powers of C here. And what we compute in the bulk using our Wilson line is this 2-point function. These we call the anomalous dimensions. And here we update our SL2R solution in the bulk from just L1 to a generic solution of with asymptotically ADS boundary conditions. This T of Y function gives us all the asymptotically ADS solutions. So we evaluate the matrix element within high phase state and the singlet state here. But what we do, in effect, what we need to do is do pattern over bulk gauge fields. But what this amounts to is just replacing the strings of these T functions with the corresponding correlation functions of stress tensors in the CFT2. So we need to do regulations of this, and one can do that by demanding word identities. Thank you. Any questions? Thank you.
So laser pointer, and then next.
Yes. Okay, thank you for all coming to the talk. I'd like to tell you today about a holographic duality for OPE blocks. So to begin with, I'll define what that is. We often use the OPE in a CFT to expand a product of operators in a local basis of other operators. But most of this expression is fixed by symmetry. So we can repackage up the part that is fixed into a new operator and give it a name. So an OPE block packages up the contributions to the OPE from the conformal family of a given primary. Now, if that primary OK is a CFT scalar, then we know that its dual in the bulk is a scalar field, in which case the OPE block BK is dual to the scalar field integrated over a geodesic. This is a believable duality because the OPE block depends on a pair of points on the boundary, and so does the geodesic. This has been proven for pure ADS, where there's one unique geodesic for any pair of space-like separated boundary points. But it's not at all obvious that it should hold in more general spacetimes, because more typically we have non-minimal geodesics and the correspondence is not one-to-one. I'd like to explore if there's any sense in which this duality still holds for more general spacetimes. So I'll look at a quotient, in fact, a conical defect, which you can construct by taking n wedges of ADS and identifying the edges of one wedge. Now, geodesics in the quotient spacetime descend from geodesics in the covering ADS space. But the geodesics that connect image points under the isometry lead to non-minimal geodesics in our defect spacetime. There's a number of changes in the CFT as well. The dual state is excited by the insertion of some heavy operator. And what this means is when we take one of the OPE insertions and move it around the heavy operator, there's a monodromy. In terms of the OPE block, we find that there's a nice decomposition into distinct contributions that differ by this monodromy. Furthermore, the CFT inherits a discrete gauge symmetry from the quotient that we've done. Of course, the full OPE block is a gauge invariant observable, but actually each of these distinct contributions is gauge invariant as well. To show how they're constructed, we can lift to the covering space of the CFT to undo this discrete gauge symmetry. In our Zn example, I'll define a partial OPE block in terms of OPE blocks in the covering theory, BK tilde. We explicitly symmetrize over them to get these partial OPE blocks. Now, there's more than one way to do that. On the covering theory, we can take our two cover operators nearby each other and then symmetrize, in which case we get one partial OPE block. Or on the cover, we can take our OPE insertions to be at an image point and then symmetrize, in which case we get a different contribution. The full OPE block sees all these contributions here. But I hope this figure makes it intuitive that the individual partial OPE blocks are dual to the bulk field integrated over a single geodesic, which can be minimal or non-minimal. So this is the sense in which the OPE block duality still holds for our defect spacetime. I think this is interesting because it gives us access from the CFT to non-minimal geodesics which reach very deep into the bulk, much past the entanglement wedge. Thank you. With causality of the boundary? Well, right, they do go beyond the entanglement wedge, but that's because they take non-local information from the whole boundary. It's as if they wrap all the way around the boundary and a little bit more. So they're collecting information from the whole boundary of the CFT, not just one small subregion. That's why they can go deeper than the entanglement wedge. All right.
There's a laser pointer up here. Forward, previous. Is that your?
Okay, first I'd like to thank the organizer for giving me the opportunity to talk. And I'm going to talk about my recent work about conformal defects and its application to holography. And this talk is based on that paper collaborated with these guys at University of Tokyo. So first, let me explain the introduction and motivation of the work. So we consider defects which are extended objects in theory, and there are various examples in QFTs, such as line operators or surface operators in gate theory. And the boundary and interface can be regarded as a codimension 1 defects. In addition, twist operators associated with entanglement entropy, QFTs, are a kind of codimension 2 defects. So why they are important and why we study as follow. So there are some progress about higher form symmetry, which are kind of defects. And they are expected to characterize the phase of QFTs. So for example, take Wilson loop, and we can distinguish the phase of theory by its expectation value. And as for another direction, due to recent great progress of the bootstrap, it is natural to think the extension of bootstrap method to defect CFT's case. To this end, we have to introduce the new OPE in defect CFT. So one is bulk to defect OPE. This is the expansion bulk local operator by the defect local operators. And when the defect is spherical, there are another type of OPE. And this is a defect OPE we call. And this is the expansion of the defect itself by bulk local operator. And this is useful to study the two-point function of defect itself. And we focus on this type of OPE. So we consider two following questions. So how can we determine the structure of defect OPE by conformal symmetry? Or how can we decompose the defect OPE into the conformal multiplet? And how can we extract the bulk ADS information by conformal defects? And the answers are as follows. So as for defect OPE, we obtained the integral representation of the defect OPE blocks by using shadow formalism as shown. And this form is pretty nice to apply for the ADS safety correspondence. Then we reconstruct the ADS scalar fields from defect OPE blocks by using Radon transform. To do so, first we identify the Radon transform of ADS scalar field with the defect OPE block when the scalar block. And by using the inversion formula of Radon transform, we reconstruct the ADS scalar field, and it actually reproduces the H-scalar formula as shown. So there are various open problems of the work, and I hope I will investigate them in future. Thank you. Okay, so let's consider the defect smearing the defect local operators on the defect. Or easiest example is a superstring. Yeah, actually, yeah. Sorry? So, which kind? I mean, in general, yeah, I mean, spherical defect in conformal field theory. I mean, yeah.
Laser pointer, previous, next previous.
All right, thank you. Let me start. So I would like to study heavy operators in conformal field theories. So in general, not much is known about heavy operators in CFTs, although some examples include Cardi formula, large charge states, and a few other examples. On the other hand, heavy operators are very interesting because, for example, they describe PV properties of gravity in ADS, black holes, thermal physics, in particular eigenstate thermalization hypothesis, and so on. So in CFTs, a natural question to ask is, what does crossing tell us about heavy operators? So let us be more concrete. And so we study a 4-point function of scalar primaries. And it has two different conformal block decompositions, which I call S-channel and T-channel. And so we take a Euclidean OPE limit when conformal cross ratios Z and Z bar go to 1. So we have some light operators in the T-channel. And we ask, so what does it imply about heavy operators in the S-channel? So it turns out that the correct quantity to consider is the OP spectral density, which is a sum over of delta functions weighed by squares of OP coefficients. And here we sum over all operators of all spins and including descendants. And for this quantity, these people derived that the large delta tails of the spectral density in the S channel is controlled by light operators in the T channel and has a universal form, which is just some power of delta in the limit delta goes to infinity, and the corrections are logarithmically suppressed. So now we can ask, so can we disentangle this sum and extract only contributions of primaries of fixed spin? So it turns out the answer is yes, and with the help of recent developments in conformal bootstrap, that's what we did. So now we have a sum only over primaries of fixed spin. And again, we have a universal large delta tails of the spectral density with the terms which are controlled by the light operators in the T channel. That's the first important point. And the second important point is that, in fact, the corrections are much better constrained than it was thought before, that all the corrections are suppressed by powers of delta and instead of logs. So that's the main result. So in fact, one can go in further and set up a systematic 1 over delta expansion. And here, the correct quantities to consider are the so-called Cauchy moments, which are just multiple integrals of the spectral density. And so roughly, the idea here is that by integrating many times, all the universal terms, they become growing, while sort of non-universal terms, which are oscillating, they stay the same, of the same order upon integration. And so you can control the corrections in this way. Finally, you can test it on some examples. For instance, in 2D Ising, the matching is quite perfect. In fact, it works well even for small delta. And there are also some predictions for 3D Ising and many other theories. And finally, let me just give you a list of the ingredients we used. So we started with writing a dispersion relation for the so-called partial waves in the complex delta plane. And then with the help of Lorentzian inversion formula and the so-called complex Tauberian theorems, we got the results. And finally, there are generalizations of these methods to potentially many other dispersion relations of this sort. Thank you.
So what would you have to say about scattering amplitudes?
So about scattering amplitudes, I guess about scattering amplitudes, so there's this old story about finite energy sum rules with which I guess string theory kind of started. You can you have something like a spectrum of resonances, which would be substitute of this spectral density, and it would be controlled by the Regge limit. I think that's roughly the picture. And with these Tauberian theorems, you can make some of the old results more rigorous.
laser pointer. This is next. This is previous.
And this one is the
Yeah.
Okay. Thank you for the opportunity to give the talk here. So I'll be talking about the modular crossing, the OP coefficients, and black holes. And this work has been done with my collaborators, Diptarko and Shobhik. So the basic premise of the talk would be 2D CFTs. As we all know that any CFT is characterized by the operator spectrum and the OP coefficients, but they cannot be arbitrary. So they have to satisfy consistency conditions like modular invariance and the crossing symmetry. And using this modular invariance, one can deduce various results, like one can deduce the Cardi-like growth of operators, heavy operators. Then if we put the CFT on a cylinder, then one can show, similar arguments show that the expectation value of a heavy operator, of any primary in heavy energy eigenstates are entropically suppressed. And similarly, one can show that there is a bound on the twist gap. There is a bound in the spectrum of the primary operators. Similarly, using crossing symmetry, one can show that there are infinite number of SL2R primaries. So the basic message is that using these symmetries, one can constrain the CFT data. So here, in the same spirit, our goal would be to find the asymptotic behavior of this 3-point coefficient, where one of these operator delta is a large delta. So it corresponds to a heavy operator. And the basic tool we are going to use is a blend of modular invariance and crossing symmetry. So we start with a 4-point function of 4 identical scalars, and we do a conformal block expansion. Now, all of these blocks have elliptic representations which become manifest in pillow geometry. To see the pillow, we considered this sphere with 4 marked points. Basically, these are 4 points where the operators are inserted. And then we do a transformation to a pillow. And the basic fact is that the cross ratio Z under this transformation becomes the modular parameter of the pillow, tau, with this relation. And if you look at this relation, you will see that the crossing symmetry basically becomes a S modular transformation on this pillow. So once we have implementation of this crossing symmetry as a modular transformation, we define a function P, which has some particular modular weight and which can be expanded in terms of this expansion. And once we have this expansion, we can easily write down the low energy data, which is basically the S channel contribution. Then we do a S modular transformation. So this trick is almost like the Cardi trick. So, and once we do the S modular transformation, we have a high energy data, which is basically the Z going to 1 limit, the T channel contribution. And the nice thing from the perspective of the S channel, the T channel contribution is dominated by the heavy states. So once we have this expression, we can do an inverse Laplace transformation to extract the F square O delta for large delta. And the answer we get is that so here basically we use the Tauberian theorem as Bauer mentioned. So this thing is entropically suppressed, and this entropy is found again by Cardi-like formula. And the main thing is that using this formula, one can show that operator product expansion converges exponentially fast. And another important thing is this is valid for all the CFTs with central charge greater than 1. Last of all, this has implication in terms of black holes. So if you consider a 2-2 scattering process with an intermediate black hole state, you expect by a phase space argument that this has to be entropically suppressed. And by IDS CFT language, this corresponds to this picture. So you expect the F square should be entropically suppressed, and this is what we find. And this is what I have to say. Thank you. Any question?
Can you find the gravity solution that describes this?
Not really. We haven't tried anything on the gravity side.
But from your arguments, using more invariance.
Okay. I guess maybe. We haven't thought about it, but I guess, so naively we started looking at this because we know that this phase space argument has this e power minus s over 2, and we saw that on the CFT side, the whole derivation is pretty clear. But yeah, from the gravity side, we haven't tried anything. Yeah. Thank you.
So laser pointer and then next previous.
The red is the pointer?
Okay, hi, my name is Talia, and I'd like to tell you about a work I did a couple of months ago with Ofer Aharoni about the TT bar deformation at large central charge. So for whoever's not familiar with the TT bar deformation, it's just taking your quantum field theory and adding this deformation, which is proportional to the determinant of the energy momentum tensor, which we can write in this form. Epsilon ik, epsilon jl, tij, tkl. And it was proven by Topological in 2004 that this is well defined, and it is also known to be solvable. So if your quantum field theory is solvable, then also by this deformation you get a solvable theory. So this motivates us to study endpoint functions. They will have to obey this differential equation. DDT of this endpoint function, you'll get the first term will be universal, that we can compute for any quantum field theory. And it will come just from like bringing down from the exponent the TT bar deformation. And then you'll have these extra terms coming from the explicit dependence of the energy momentum tensor on T. So with the initial condition that at T equals 0, you get your original theory. Okay, so if we can rewrite this det T in a way that will simplify things when we want to compute the correlation functions. So this new form, which is exactly equivalent to the original form, we see we have pk tjk, and this vanishes by the equation of motion. So once we have this in our correlation function, we can imply void identities and simplify the correlation function. Okay? So instead of getting like this n plus 2 point function that we'll have to calculate, it will reduce to n plus 1 or n point functions. So let's, okay, so furthermore, we can even simplify this calculation further if we look at the large C limit where these correlation functions factorize. So for example, if we want to compute the 2 point function, this blue term is the one that we get from bring down from the exponent. And this will factorize into two 2 point functions. Where the first one, as you can see, we have wk tjk. This is 0. We imply the word identities. And if we assume that the 1 point function vanishes, then this vanishes. So in our equation, we get that the 2 point function, ddt of the 2 point function is 0. And therefore, the 2 point function is independent of the deformation. So the 2 point function will be the same as you have in the original theory. OK, now we can go to the 3 point function. And the 3 point function will have we'll have to calculate this 3 point function. And again, we apply the word identities, which will give you a sum of 2 point functions. And then you'll have a product of 2 point functions, two 2 point functions. And the 2 point function, as we learned, is independent of T. And then our differential equation will give you that the 3 point function will be linear in T. Moreover, it will also have a C square dependence that you can calculate. So generalizing this procedure, we get that endpoint function will be dependent on T to the power n minus 2, C to the power n minus 1 at large T. And it's like a recursive relation that once you compute, you can compute it order by order in the endpoint functions. So to conclude, we found a way to compute endpoint functions in the deformed quantum field theory And the behavior is controlled just by knowing, once you know your two-point function of your original quantum field theory, then you know all the rest. Thank you. Yeah.
So I guess there's supposed to be a holographic dual to PP bar deformation.
Right.
I guess in that one could also compute endpoint functions of the stress tensor.
I guess so. I didn't get to do the holographic computation, but I know some guys like Kutasov and Amit, they conjectured an operator for this TT bar deformation, and perhaps we could look at that.
There's a laser pointer, and then it's next previous.
Hi, I would like to thank the organizers for giving me the opportunity to present my work today. My work is done, I'll be going to present my work which is part of these two papers and some ongoing work with a lot of my collaborators. Chern-Simons theories in 3 dimensions are rather interesting because of the wide variety of applications they find in various areas of physics. And they seem to have some rather interesting properties, one of which is the fact that they have these conjectured strong weak coupling dualities. In particular, the n equals 2 Chern-Simons theory coupled to fundamental matter has been conjectured to have, is conjectured to be self-dual under the following mapping of the parameters that appear in the Lagrangian. And up till this point, this conjecture has been verified by explicit computation of thermal partition functions, correlation functions, and 2-to-2 scattering matrices. However, in our work, we wanted to verify this conjecture, establish this conjecture more concretely by computation of arbitrary n-to-m scattering amplitudes. And the first step in that direction would be the computation of tree-level scattering amplitudes. So in the first paper, we have shown that in these in the n equals 2 Chern-Simons theories, we can recursively compute any arbitrary n-to-m scattering and tree-level scattering amplitude in terms of 2-to-2 scattering amplitude. And these recursion relations, which go by the name of BCFW recursion relations, rely on the singularity structure of the tree-level amplitudes and on analytically continuing the external moment of the particle into complex plane, and such that the overall momentum conservation still holds true and all the particles are still on shell. So here what I'm displaying is an arbitrary 2n point function written in terms of super amplitudes, which has been decomposed recursively in terms of the left amplitude and the right amplitude. And you can just keep on doing this so that finally you have the expression only in terms of the 4-point function, 4-point amplitudes. What's more, in our work, we could also find out a recursive relationship for the pure non-supersymmetric theory, which is fermion coupled to Chern-Simons, and which was rather interesting because a priori the fermionic theory coupled to Chern-Simons does not satisfy the requirements of BCFW recursions, but using the supersymmetric word identities, we could compute the using the supersymmetric amplitude, we could compute the amplitudes just in the fermionic theory only. These theories have another rather interesting property which was found in this particular paper, which was that the 2-to-2 scattering amplitude is tree-level exact in all but one channel, in which it gets renormalized only by an overall multiplicative factor, which depends on the Tuft coupling in theory. In our experience, such non-renormalizations often point towards existence of some symmetries, and our subsequent work is directed towards finding these symmetries. In our second paper, what we found was that if we write the 2-to-2 scattering amplitude in terms of the dual variables, which are defined in terms of the external momenta in this particular fashion, then this 2-to-2 scattering amplitude is invariant under application of these superconformal generators, which are written in terms of these dual coordinates. And this symmetry is known as dual superconformal invariance. So I would like to end with some directions for future work. And one of the things that we are trying to work on is trying to see whether this dual superconformal invariance generalizes to higher point amplitudes. And there are some other things that we are also interested in, which includes trying to compute the exact loop level amplitudes for arbitrary point scatterings. Thank you.
Let's thank all the speakers again.
Thank you.